Now that we've explored a little bit, looking at angles as central angles of circles, we're going to look to maybe apply this in order to do two things: measure the area of a sector of a circle, and also to measure an arc length on a sector of a circle here. So the very first thing we're going to do is we're going to kind of indicate that we're going to look for the arc length, and area of a circular sector. So the very first thing I want to do is just go ahead and kind of acknowledge this sketch over here, and you can certainly make this on your paper. This is pretty easy to do. What we're going to do is we're going to draw in a central angle, and so this angle doesn't have to be any particular size. But the things that I do want to indicate are these things here. This circle is of radius r, no matter which radius you look at. It has a central angle theta, and it has some arc length out here. We say that this arc length, this distance, is this distance s. So previously, what we had seen is that in a circle with radius r, this central angle in radians is measured by telling us how many times the radius length fits into the intercepted arc. And so what I'm going to do is I'm going to go ahead and put our formula over here for the angle in radians. We say that it's our arc length divided by our radius length right here. The neat thing about this relationship is that sometimes, maybe we want to know the angle, and we can take the arc length and divide it by the radius, but maybe it's two other things that we know about this relationship, and we want to find the third. So for instance, if this is a situation where maybe what I want to do is calculate an arc length, it would be really easy to do if I knew the length of one radius, and I also knew the size of my angle in radians, okay? So what we're going to do is we're going to take this formula, twist it around a little bit, and we're going to solve for s. And in order to do so, what we do is we multiply both sides by r. And what this does is it gives us what we call our arc length formula that I want to have you write down. So our arc length formula is just simply s equals r theta, or I'm going to write theta r. And so this is our formula that just says, look, if you know the radius and you know your angle, as long as your angle is in radians, then you can take your angle and multiply it by the radius, and dude, you get your arc length, okay? Another formula that I'm going to have you write down is also referred to as what we call the sector area. And the sector area is somewhat similar to our arc length formula here, but our sector area is really just representing the area that is occupied by this circular sector that is rotated through theta radians and has a circle of radius r. So our sector area, we're going to write area, or A equals 1/2. We're going to write theta r squared. So in terms of similarity, the sector area formula here looks like it has a half in front of our theta and r, and it looks also like our r is just squared. But these are a couple of formulas we want to make sure that we have in our back pockets. You'll notice here, and this is something you want to write down, is just this. For arc length and sector area, the angle theta must be in radians. So that is to say that if it is not in radians to begin with, that's something we're going to take the time to convert into radians here. So let's take a look at an example of where we might be using this rotational trig. And so I look at a situation here where it looks like we have some softball field. It says a softball field forms a sector with the dimensions shown. Find the length of the outfield fence and the area of the field. One thing to kind of keep in mind is when we look at these areas of sectors problems, we don't always have to have the entire circle in order to do this, but you might look at this as a circle of radius r that had some central angle theta and some arc length s. It's just that within our context of this problem here, it looks like our circular sector here, in terms of what we know, has a radius of 200 feet. Okay. I'm going to make sure I write that down here. The other thing I notice is our angle. Our angle is 90 degrees, so please make sure you write that down as well. We're going to need both of these measurements here in order to calculate arc length as well as our sector area. As it happens, this is just going to be plug and chug. So in a moment here, in order to find the arc length, we're just going to say the arc length is equal to our radius times our angle. The only thing here that we have to be careful of is that your angle has to be in radians. So with respect to 90 degrees, what is this in radians? Let's go ahead and convert this by taking it times the appropriate conversion factor here, which in this case is pi over 180. We can go ahead and drop our units of degrees. 90 and 180 both share a common factor of 10 since they both end in 0, and 9 and 18 both share a common factor of 9, so this becomes a 1. This becomes a 2. Looks like we get left with pi times 1 over 1 times 2. We get pi halves radians. So that is to say that we have to include pi halves here and our our arc length formula. And in this case, we're going to treat this as just multiplying fractions straight across. Looks like we get 200 times pi. And this is all over 1 times 2, which we can see that this would reduce even further. We say 100 pi, and we need to make sure we label this because this was a distance, a length. We're going to have to use the same units that we use in our problem here. So 100 pi feet, and while we're at it, let's go ahead and get a calculation for this. So using your calculator here, typing in 100, and your pi key is kind of behind your caret key if you're using a TI. 100 pi would be about 314.16. So about 314.16, and this is in feet. So that would represent this distance around the outfield fence right here that we wanted to find. We also want to find the area of the field. So I'm going to kind of scroll down a little bit here. Again, this is just going to be plug and chug. So we're going to say area. And we know our area is 1/2 theta r squared. If you wrote that down, good. So our theta has to be in radians. Well, we've got this in radians. So let's go ahead and fill this out. We've got 1/2. Our theta is pi halves. Our radius is 200 feet, and this is squared. So let's go ahead and do our order of operations here. It looks like it's important we start with our exponent. And so if we square out our 200 feet here, I suppose we would get 1/2 times pi over 2 times this would be a 4 with 1, 2, 3, 4 zeros in it, and this would be square feet. And I'm going to put this over 1. Square feet because we're taking feet times feet. At this point, again, we can just multiply straight across. We would get 4, 1, 2, 3, 4 zeros, pi, feet squared, all over 2 times 2 times 1, all over 4. So this is the same as 1 with 1, 2, 3, 4 zeros, pi, feet squared. And this would be our exact value. Again, we could just take this 1 with 4 zeros and multiply it by pi. We get like 31415.92. So 31415.92, and this would be feet squared. With these kind of problems, you'll want a decimal and an exact value here. So just know that these two formulas exist and that you will need to use them. And they're really not so bad to use if you can identify the, I suppose, the angle of rotation and the radius. You just got to make sure that your angle is in radians. Cheers.